Hello everyone, I'm Musa. I would like to talk about our new proposed level shifter in which a closed loop negative feedback is utilized to minimize two significant parameters of propagation delay and power consumption. Welcome to my presentation. I organized my speech as you can see here: introduction, proposed fast level shifter, circuit implementation, simulation result, performance comparison, post level simulation, layout, conclusion, question. A level shifter is a key circuit in many applications such as power converter and biomedical implants. It translates one logic level to another, allowing communication between the circuits that operate at different voltage level. The conventional topology of the level shifter suffers from severe contention during transition. It is particularly severe because of the sequential nature of operation of the level shifter. To stop a short circuit on one side of the level shifter, the output level on that side must first be pulled down to open the PMOS on the other side, and thus pull the complementary output up and close the circuit. In the right figure, operation with contention and proper contention is illustrated. Many structures have been developed to mitigate or eliminate the generated contention during transition. These structures are based on three common basic circuits: latch, current mirror, and comparator configurations. The latch-based design suffers from weak pull-down in low VDDL, in addition to extreme contention, while the current mirror-based tolerates the exceedingly static power consumption. Although in the comparator-based configuration, the overall power consumption is improved, it endures contention. Besides, it is not an area-efficient structure. One simple improved version with passive isolation of the gates to pull quickly down the top transistor is presented. Active isolation of the gate can achieve a better result as another solution. A current limiter for latch-based topology has been employed to limit the current flow during transitions. Here, the timing diagram of propagation delay presents. The proposed level shifter topology is based on the current mirror approach, which has been modified for its simplicity and efficiency. The presented design involves a closed loop negative feedback circuit to control the amount of conveyed current to the level up shifting part, and thus helps in decreasing the power consumption and the propagation delay. VA is the output node, which later is used to make the controlling voltage, VSC. The feedback network measures the variation of voltage delta VA and converts it to current variation delta IA. Then delta IA is subtracted from the main mirrored current I1, where the resulting current I is injected to level up shifting structure. So in the case of delta IA equal to I1, the controlling part will totally turn off the circuit. Consequently, the average corresponding energy of green highlighted volume in this figure would be saved in each period. It should be noticed that the value of parasitic capacitances in node VA is considerably larger than that the size in the next stage. Therefore, putting feedback network in this node to gradually shift the level up by limited charge discharge of large parasitic capacitance in node VA, and then convert it to VDDH in lower strength nodes by little contention would improve both power consumption and propagation delay significantly. For better clarification of circuit operation, this figure is allocated. The VCCS provides a dependent current to SSM and generates a voltage VA, which in turn contributes in making controlling voltage VSC for feedback network. And then VA is buffered to reach VDDH voltage. Beneficial achievements by the proposed fast level shifter are: compared with conventional latch-based level shifter, the proposed topology doesn't involve pull-up and pull-down networks. Therefore, the strength pulling up in opposite of weak pulling down is totally removed, which leads to the drastically improvement in both propagation delay and power consumption. Second, contrary to traditional current mirror-based level shifter, where the standby current affects the level shifter operation, the feedback network in this proposed circuit allows the level shifter to operate only in certain time slots. Thus, in the off operation periods, the circuit is in a sleep mode, which results in essentially decrement in the leakage current. Consequently, the static power is substantially limited. Compared to the conventional comparator-based level shifter implementations, the presented circuit is realized by few transistors, and this results in an area-efficient design. The transistor level of the proposed level shifter circuit present here. It is composed of some sub-blocks, including SSM, VCCS, controlling closed-loop negative feedback network, input inverter, and output buffer. Since the input pulse in is applied to MN1 and the input of MP1 and MP2 is the voltage of VA, which is in phase within, and this building block is permitted to work only in the duration of propagation delay. In the other time, VA will turn off MP1 and MP2 to avoid the flowing of current to SSM, which called sleep mode. When the in is going up, MN2, MN3, and MN4 are turning off. Consequently, the available current in the branch of SSM are reversing to contribute with the flowing current in P-type MOSFETs, MP2 and MP4 for charging of the available parasitic capacitance in the node VR. So the potential of VR in this limited short time is shifting up gradually. The potential progress of VA is kept until both MP1 and MP2 reach the cutoff region. Finally, the output buffer converts VA to VDDH easily. In the proposed topology, the generated current from MN1 is mirrored to SSM for shifting up the output voltage. However, the float current in MP2 and MP4 depends on VA source gate of MP2. Actually, when VR is gradually going up, the gate of MP2 follows it, while the drain of MP2 is going down. As a result, VS source gate of MP2 and VS source drain of MP4 are decreasing. In other words, a dependent current flowed in the SSM by a VCCS in which the VSC are VS source gate of MP2 associated with VS source drain of MP4 as well to create a voltage in VA as much as the circuit is needed to avoid extra power out of control dissipation. It means that the closed loop negative feedback saves a considerable amount of energy. Here, the simulation results presents via A input voltage, fluid current, and propagation delay tagged in the figure. Propagation delay of 1.99 nanosecond control the delivered current flow only in the short limited time of propagation delay. In addition, it shows the slow progress of VA that is controlled by closed loop negative feedback network, and the output voltage, which is the buffered voltage at VA. Since the duration of fluid current is limited, the average of fluid current in the SSM is around 183 nanoampere. For performance comparison with similar works, delay versus VDDL and Schmuck plot are prepared. The minimum and maximum propagation delay of the proposed level shifter are around 900 nanosecond at VDDL equal to 0.4 volt, at 1.9 nanosecond at VDDL equal to 1 volt respectively, which are comparably better than similar works. Compared to the operation of the level shifter performance reported in reference 11, which is limited to 100 MHz, our design operates up to 225 MHz. This table summarizes and compares the performance of the proposed circuit with similar designs. Different figures of merit have been applied to provide a fair comparison. In the first figure of merit, the best value is the lowest one. In the second figure of merit, the best value is lowest one. And in the last figure of merit, the best value is the largest one. As it is shown in the table, the proposed level shifter achieves the best value of figure of merits compared to the prior works. This ensures the best performance of the presented design. The equation of figure of merit presents here. Post-layout simulation results presents here input voltage, output voltage, and propagation delay tagged in the figure. The layout of proposed level shifter presents in this slide. As you can see, the core occupied only 25 micrometer cross 25 micrometer of silicon area, and around the core there are the supply pads and I/O pins. As the conclusion, the previous level shifter were based on latch, current source, and comparator. In the proposed level shifter circuit, a closed loop negative feedback circuit is added to control the delivered amount of current to keep down the rate of charge discharge of parasitic capacitance for attaining lowest propagation delay and power consumption. The main advantage of proposed level shifter summarizes here. The propagation delay equal to 1.99 nanosecond and energy consumption of 0.5 picojoule are successfully achieved. Finally, I would like to thank you for your attention. If you have any question, I am pleased to answer.